Good morning, everyone. Hi, I am Aniket, and I am a PhD student from Department of and Computer Engineering at University of Iowa. And today I will be presenting my work, Joint Calibrationless Reconstruction and Segmentation of Parallel MRI. So neurodegenerative disorders like Alzheimer's, when they progress, then there is severe shrinkage in important brain regions like hippocampus. So for that, you need to track the volume of such regions. And in order to do that, you need a really high resolution brain MRI scan because there are really small subfield regions in the hippocampus. And for that, you would require a 0.25 mm isotropic resolution scan, which is really high and takes 8 hours long. And that is really troublesome for people. The challenges is prolonged acquisition times, and such scans are more vulnerable to motion artifacts due to patient movement. So a solution is to have a reconstruction algorithm to recover images from a fast undersampled acquisition. So in that case, an undersampled acquisition would have samples collected at fewer locations, and therefore you need a reconstruction algorithm to interpolate the unknown ones and get a good quality image. However, the challenge with existing reconstruction algorithms is that they are effective only at low acceleration factors, they are sensitive to motion artifacts, and have high computational complexity. This is the reconstruction and segmentation pipeline. And if you have a reconstruction algorithm to have an undersampled acquisition, then you need to have a good segmentation algorithm which is robust to motion and undersampling artifacts, and also robust to errors from reconstructions, and also provides good quality segmentations. And the performance of segmentation algorithms depends heavily on the reconstruction quality. So the goal of my talk is to provide a goal of my research is to develop a novel MRI image analysis pipeline where I would have reconstruction and segmentation both tasks jointly optimized together. So this is the outline of my talk, where I will talk about the background of my research, and then I will introduce the framework and talk about results and conclusion. So parallel MRI has multiple receiver coils, which are spatially sensitive to different regions of the organ scan and hence can achieve high acceleration factors. It often requires calibration scans on top of main scans to get the sensitivity profile of those coils. Recently, deep learning approaches were introduced, which can be broadly categorized into direct approaches and model-based approaches. Direct approaches uses a huge CNN with a lot of training parameters to map directly the undersampled image to a fully sampled one, and it requires huge number of training samples, which are very difficult to get in many applications. On the other hand, model-based deep learning was introduced, which is inspired from compressed sensing. It has a data consistency term and a CNN as a prior, and it alternates between the two optimization blocks. One enforces physics-based data consistency, and the other one is a CNN-based denoiser. This is unrolled for finite number of iterations and trained end-to-end. Parallel MRI recovery methods can be classified into calibrated and uncalibrated methods. Calibrated methods rely on calibration scans uh, to estimate coil sensitivities, and those methods are pre-calibrated methods. Some methods estimate coil sensitivities from the fully sampled center of K space. Those are called self-calibrated. On the other hand, calibration-less methods are structured low-rank methods, which do not rely on coil sensitivity information, and rather they construct a low-rank matrix and penalize its rank based on some linear annihilation relations followed by the signal. And these methods are relatively insensitive to motion artifacts and do not require fully sampled calibration region in the center, and hence can achieve higher acceleration factors. So let's look at some of the annihilation relations by SLR methods. Suppose you have coil images gamma 1, gamma 2, they satisfy some annihilation relation as shown here. This is multiplicative in image domain and translates to convolution in K-space. And that can be written as matrix multiplication. And that gives rise to a linear convolution block, which has convolution filters. So in our group proposed a K-space deep SLR network where instead of having a linear convolution block, we replace it with a CNN block, which is a nonlinear convolution block, and use it in model-based setup where we combine it with a data consistency block and the network alternates between these two, which is unrolled for finite number of iterations and trained end to end. So goal of my research is to come up with such a calibration-less MRI reconstruction strategy and also jointly optimize for segmentation so that both the tasks help each other and perform better. And in the end, we have good quality reconstruction and also a good quality segmentation, which is much more robust to undersampling and motion artifacts. So I come up with a novel image domain deep SLR framework. I also propose a joint reconstruction segmentation framework to improve both the tasks. And I also study the framework for training it with fewer shots of segmentation because often segmentation labels are not available for a lot of applications. So let's look at image domain annihilation relations. Suppose you have n coil images gamma 1 to gamma n, and you are looking at patches centered at C of dimension m by m. So you extract patches, and if you assume the coil sensitivity is smooth in that area, then those patches, uh, when they are stacked together, they form a low rank matrix gamma C. There are several such matrices, and we pose the optimization problem as minimizing the sum of those uh, lifted matrix from the patches and also the data consistency term, which enforces data consistency by maintaining the physics of the data acquisition. And we obtain a network where we have a image domain CNN, and that alternates with the data consistency block. And this is unrolled for finite number of iterations and trained end to end. This is our proposed image domain deep SLR network. We combine it with a segmentation decoder, SID, for performing a segmentation task. And this decoder is attached to the CNN in the last iteration. And that the CNN in every iteration is like autoencoder architecture, and the encoder of the last iteration is attached to the segmentation decoder as well. So, so as a result, we have a shared encoder architecture, which makes both the networks regularize each other. And going forward, we find that it helps in reduction in segmentation errors from undersampling artifacts. This is the combined training loss, where you use mean squared error loss for reconstruction and cross entropy loss for segmentation. And the weights are shared in the reconstruction network, the weights are shared across iterations. That is an important point. So now we also test this framework for training it with few shots for segmentation, where we assume labels available for only 10% of the subjects. And when data sets are without segmentation labels, we train it with reconstruction loss. And when data sets are with labels, then we use the combined loss. The shared encoder helps segmentation network to rely on fewer examples for training. Now, these are the results. So these are the results, reconstruction results on six-fold accelerated data, and we can see that proposed IDSLR is doing better than the other methods. K-unit is a K-space unit uh, for directly mapping it into a fully sampled reconstruction. KDSLR is the K-space deep SLR from our group that I talked about. KikiNet is an unrolled deep learning algorithm which alternates between image domain and K-space CNNs. So the proposed joint architecture is performing reconstructions even better than the IDSLR alone network, reconstruction alone network, which shows the benefit in adding segmentation tasks. Similarly, we also compare the segmentation performance of different joint architectures. SEG is the unit-based segmentation network. IDSLR plus SEG are a cascade of IDSLR and SEG networks trained separately. And the cascade networks are basically IDSLR and SEG trained jointly end-to-end. And we found that in terms of dice coefficients of CSF, cerebrospinal fluid, gray matter, and white matter, we find that our proposed approach is doing much better than the other ones. We also compare our joint architecture with the shared encoder architecture, which is JRS. This is another shared encoder architecture where you have shared decoder encoder shared at every iteration, and you combine segmentations from each iteration and compute the loss and try to optimize the parameters of your network. So even in this case, we found that the proposed approach is much better in terms of reconstruction and segmentation performance. So we introduced a novel image domain deep learning approach for calibrationless parallel MRI recovery. We found it to be doing better than the case-based deep learning approach. And the proposed shared encoder architecture is doing much better in terms of segmentation and reconstruction than other methods. And also it uh, in case of fewer shots for segmentation, its performance is uh, at par with all the other methods. So shared encoder architecture helps to improve both the tasks and make segmentation network less reliable on training examples. Thank you.